Even and odd functions. A graph is symmetric if one half looks like the other half. We might also say that one half of the graph is a reflection of the other. When a graph has symmetry, we usually say that it is symmetric with respect to a line or a point. Okay, the graph in figure 315 is symmetric with respect to the x-axis because the half of the graph above the x-axis is a reflection of the half below. Let's take a look. All right, so right here we have the graph, and the x-axis is this axis right here. And that acts as a mirror. Okay, so this half of the graph and this half of the graph are reflections of each other. So basically the x-axis acts as a mirror. So this is a reflection of that and vice versa. The graph in figure 316 is symmetric with respect to the y-axis. Let's take a look. All right, so right here, the up-down portion is the y-axis. And this acts as a mirror. All right, and you can see here, if you look at this half of the graph, it is a reflection of this half of the graph. And vice versa. They are mirror images of each other. The graph in figure 317 is symmetric with respect to the vertical line x equals 2. All right, here's figure 317. This is the x-axis. Right here is x equals 2. The line equation of x equals 2 makes this line here. Okay, that's x equals 2. And as you can see, the reflection on the right-hand side and on the left-hand side are the same. Okay, this line here acts as the mirror, so it's reflected. One type of symmetry that's a little harder to see is origin symmetry. A graph has origin symmetry if folding the graph along the x-axis and then along the y-axis would have one part of the graph coincide with the other part. The graphs of 318 and 319 have origin symmetry. So look at figure 318 right here. We have these two curves. If you took this curve and you folded this graph paper along this axis over here, this curve would appear like so. All right, and then if you folded the graph paper along this axis right here, this curve here would appear as so right here. All right, so you take this reflected over the y-axis, take this reflected over the x-axis, and you have a trace over of the original. So these two have origin symmetry. All right, same here with this graph. If you took this and you used this as the mirror, and you took this graph paper and folded this over, okay, what you would have is this graph right there. You'd have the reflection. Okay, and then if you took the paper and folded along the x-axis, this would be the mirror, and this would reflect and go back to the original, which is right here. Okay, so again, origin symmetry means reflected over the y and then the x, or vice versa, x and then the y, same thing. All right, so knowing in advance whether or not the graph of a function is symmetric can make sketching the graph less work. We can use algebra to decide if the graph of a function has a y-axis or origin symmetry. Except for the function f of x equals 0, the graph of a function will not have x-axis symmetry because x-axis symmetry would cause a graph to fail the vertical line test. All right, remember the vertical line test is to test if something is a function. All right, if you remember that. For the graph of a function to be symmetric with respect to y-axis, a point on the left of the y-axis will have a mirror image on the right side of the graph. Okay, so this basically is what an even function looks like. And here are the characteristics. An even function has y-axis symmetry. All right, notice this y-axis right here acts as a mirror. Okay, this part of the function that's on this side is the same as the part of the function that's on the other side. And also, for any point on the graph x comma y, the point negative x comma y also exists. So if you look at this point right here, this is 1 on the x and 2 on the y. Okay, that's 1 on the x and 2 on the y. And this point right here is negative 1 on the x and 2 on the y. So basically, the y-coordinate is the same, but the x is the negative version of itself. And that's what we have here. The y-coordinate is 2, but the x-coordinate is negative 1 and positive 1. Okay, finally, if you have the actual equation, what you want to do is plug in negative x in place of x. And if you get the same equation as the original, that's how you know it is an even function. Okay, we're going to do a few problems in a minute, but this is the main characteristic to prove it's an even function if you have the equation. Now for the odd functions, first off you have origin symmetry. So we said what that meant before. Okay, if you took this part of the graph and reflected it over the x-axis, you would have this right here. And then in turn, if you reflected that over the y-axis, you'd have this right here. So in other words, you fold it 2 times over the x and y-axis and you'll get the original, or it'll map over the other part of the original graph. All right. Also, any point x comma y maps to the point negative x comma negative y. So let's see. This point right here is x comma y. And if we were to do negative x and negative y, change the sign on this, you would have 8. Change the sign on that, you would have negative 2. And as you can see, we have that right here. So you change the sign on both the x and y coordinates of a point that's on the graph, and you'll have another point that's on the graph. That's another way to prove origin symmetry. Okay, finally, if you have the function equation and you plug in negative x in place of any x's, you should get the negative version of the original function. All right, so again, we're going to do a few problems like this and prove if it's even or odd or neither. Now, one thing you want to remember, if you have a negative number or negative x and you raise that to an even power, that x is going to become positive, okay, because negative times negative is positive. However, if you have a negative x with an odd exponent, that x is going to stay negative, and that negative just gets moved out front. So negative x, a times negative x is negative ax if it's an odd power. All right, so for this example right here, we're going to say if it's even, odd, or neither. Okay, so we'll call the test to see if it's an even function. You plug in negative x in place of x and see if it returns the original function. If not, then move to the odd function test. You plug in negative x and see if it returns the negative version of the original function. All right, so we have f of x. Let's find f of negative x. And that means we plug in negative x in place of x. So instead of x squared, it's going to be negative x squared. Okay, make sure you use parentheses, and that's minus 2. And when you square negative x, it becomes positive, and it's just x squared, and that's minus 2. Okay? So that is the same as the original. So f of negative x is the same as f of x. And we said if it returns the original, that means it's even. All right, once again, we want to see if this function is even, odd, or neither. Okay, so the first test is to do f of negative x. That means we are plugging in negative x in place of any x's. All right, so x to the third becomes negative x to the third. Use parentheses, plus 5. Instead of times x, it's times negative x. All right, so negative x to the third, remember, if it's an odd exponent, the negative sign remains because negative times negative times negative gives you a negative. All right, so negative x to the third stays as is. 5 times negative x is negative 5x. All right, so this is f of negative x. Does it equal f of x? Well, this is completely different than the original, so it's not even. All right, let's try the odd function test. We already have f of negative x. The odd function test is to do the negative of f of x. So that just means you multiply the whole function by -1 or distribute a negative sign. So negative f of x, we have our negative sign, and that is distributed to the original function f of x. All right, so that's x to the third plus 5x. As you can see, all I did was recopy the original. Okay, and there's a negative sign that gets distributed. So negative x to the third and negative 5x. And that is negative f of x. And it matches f of negative x. So as a result, f of negative x equals negative f of x, and it is odd. All right, so we're going to do more, but a quick summary. If f of negative x equals the original, it's even. If f of negative x equals the negative of the original, it's odd. Okay, and if neither of them work, then it's going to be neither. All right, so let's try and see if this is even, odd, or neither. All right, so the first step is to do f of negative x. Okay, so wherever there's an x, right here and right here, we're going to plug in negative x. So negative x is in the numerator, and negative x plus 1 is in the denominator. Okay, and does that equal the original? No. Does that equal the original? No, so it's not even. All right, let's try in a different color here. The negative of the original, negative f of x. So we're going to take the negative of the original, x over x plus 1. So how would we distribute this negative? Well, you can just distribute it to the numerator. It's going to be a negative x over x plus 1. And does that equal f of negative x, which we found right here? No. So it's not odd either. Okay, this is what we got for f of negative x. All right, and it does not equal the original. And this is what we got for negative f of x, and it doesn't equal f of negative x. It doesn't equal that one right there. Okay, it's not odd, it's not even, so that means it's neither. All right, generally speaking, when you distribute a negative sign to a fraction, it goes to the numerator. Okay, and right here, even if we wrote this one in a different form, let's say you factored out a negative sign, and that means you would change the sign on the numerator, and this would be a positive x divided by, instead of negative x plus 1, it should really say 1 minus x. And yeah, that would just be negative x divided by 1 minus x if you wanted to put it in a different form. Okay, but either way, it does not equal the original.